Okay, so hi everyone. Today we have the pleasure of welcoming Gaël Servignat from the Laboratoire Astroparticule et Cosmologie in Paris. He's a postdoc there. And Gaël is going to speak about OXAS, the spectral code for isolating neutron star oscillations. So feel free to ask questions during the presentation, and there will be also time at the end. So please, Gaël, you have the floor.
Thank you for the introduction. Okay, so as Jean-Baptiste just mentioned, I'm going to tell you about this code that I've been developing during my PhD. So there is a bunch of, let's say, keywords in there. A lot of them are about the technical stuff that there is inside this code. So we'll try to guide you through this, why we chose to write the code this way, and what's the purpose of the code. So basically, as it's written there, the point will be to show you how I want to produce oscillation modes for isolation neutron stars, and also gravitational wave signal. Okay. This way. Right. Okay. So first, why are we interested in gravitational waves and where do we come from? So in 1915, Albert Einstein published his theory of general relativity. At this time, gravity used to be a force, but then Einstein had this genius idea to say, okay, maybe this is not what we think it is, and say that space-time is a thing. We put them together, and now gravity is what is going to have an effect on space-time itself. Then 1 year later, he said, okay, what happens if we are in a weak field? And he shows that if you do that and you have moving and accelerating masses, you can have waves. So this is not something that propagates in the space-time, but it is a propagation of space-time itself. At this point, it's just a theory. But then a few decades later, the astrophysicists Hubbs and Taylor, they see in the sky a binary system. Well, I wrote that it's a pulsar, but at this time they didn't know yet. But what they do is that they measure the orbital period of this binary system, and they realize that this period is decreasing by approximately 76 microseconds per year. And they say, ooh, maybe this is gravitational wave emission. So they confront this with the theory, and they find that indeed this sticks perfectly to Einstein's theory. The measurements have been continuing for some time after, and it is still astonishingly well with the theory. So this was the first indirect detection of gravitational waves. So we say, okay, we think that they actually exist. So now we want to try to see them directly. So people have been building detectors, very big ones. So you may know them as the LDK collaboration. But there was LIGO in the late 90s. And in the early 2000s, the Virgo detector was also inaugurated. And then after 15 years of instrumental development, there was the first detection of the binary reduction. So how do they do it is, let's say, really technical. But the thing is, there are several stages of the life of binary of compact objects. So first you have this spiral phase, the one that was detected by Taylor. They orbit around each other, lose energy because of this gravitational wave radiation, and then at some point they will merge. And when that happens, there is this chirp. The frequency of the orbital motion increases up to this merger, and then the rebound is the end of the cycle. And actually, this is exactly what was observed when this first event in 2015 was seen. And then 2 years later, there was the first detection of the binary neutron star coalescence, which was accompanied by what is known as the electromagnetic counterpart. So there was a burst exactly at the sky localization of the event. And to this day, the LDK collaboration has a public catalog of approximately 90 compact fluorescence events. And there is a fourth observation campaign ongoing, which is actually going to its third phase soon. And I think in the end of the year. And they have detected a lot more of them. So at this point, we say that gravitational waves, they do exist. We know how to see them. And the point is, okay, we can extract information, astrophysical information from the sources of gravitational waves. Right. So I'm going to talk about numerical relativity in this talk, and the reason why is because we want to do numerical simulations of these binaries, because the Einstein equations that describe gravity are not solvable in, I mean, you cannot analytically solve them in realistic configurations, so that's result to your computer. And the idea of numerical relativity is to do this numerically. So there was a lot of effort done in the past decades, and we went from just simulating a spherically symmetric fluid collapse to a black hole in the 60s to the first binary neutron star, then binary black hole, and neutron star binary black hole mergers in the 2000s. And this has been permitted by several things. Let's say that I'm not going to go into the details of this, but I'm going to introduce shortly after the hydrodynamics of wireless waves. So my expertise is in the neutron star side of this thing. Right. So I have been talking about neutron stars a lot. And what are they? So basically, the easiest way to think about how neutron stars are born is to remember that the main channel of formation is the collapse of a massive star, and massive means above 8 solar masses. And during this cataclysmic event, the matter will be neutronized thanks to this nuclear reaction. A lot of neutrinos will be emitted in the process, by the way. And in the end, what you have, after some other processes like cooling and other stuff, you get an object, an astrophysical object, which is approximately the mass of the sun. And I would like to say that it is the size of Paris. So you put the whole sun just in Paris. And what you can measure and so how you say that this is very relativistic object is what we call complexity. It's compactness, I never remember. Right, so this ratio between mass and radius. And for your typical neutron star, this is, say, something like 0.2. And actually, if you think about this quantity for a black hole, it's 1/2. So neutron stars, they are the last object that can form before being a black hole. They are the most compact that you can find before having a black hole. And the point of neutron stars is that they are so dense that they reach inside densities that we cannot see or reproduce enough. So being able to probe the inside of this neutron star would give us a lot of information of what happens in the really high density regimes and rather low temperature part of nuclear matter properties. And the point is that you have several layers. There is an atmosphere, but inside you have some crust, in which we more or less know what happens. But very quickly, after a few hundred meters, we don't know what happens, and there are a lot of models. People have ideas, of course. But if we were able to detect gravitational waves coming from the neutron star, we could probe it inside and say, oh, okay, maybe this model is better than the other. This one is not really normal. But I'm going to find out. Right. And so, as I said before, we want to do numerical simulations. So we have to, on the one hand, solve Einstein equations, but also hydrodynamics. And so, yes, let me first explain also the different parts of the life of the binary neutron stars. So I have put again a bunch of milestones. So the first neutron star was detected in the 60s by Joseph Gaël. You might know the story that they first thought maybe, oh, this is some extraterrestrial message, but no, it was precisely human or whatever. It was, of course, astrophysical. And then you know the story that the PhD advisor of Joseph Gaël got awarded the Nobel Prize, but not her, which can trigger some discussion. There is this binary pulsar by Hansen Taylor. Then in the 80s, there was the first formation detection. So we saw 12 neutrinos. This is compatible with the neutralization of approximately 1 solar mass. I think there was, by the way, some breakthrough on these events that people figure whether it's staying in neutron star or collapse to black hole. Not sure. Right? And then 30 years later, this detection of the binary neutron star. And now, what the NBK collaboration is not able to see is the post-coalescence stage of the binary neutron star. So what is thought is that after the merger, well, something might form, which might be a supermassive or hypermassive neutron star. So why do we call it supermassive or hypermassive? Is because general relativity will predict a maximum mass. If you give it an equation of state, you will have a maximum mass. But then if you take two neutron stars and you merge them, the total mass of the resulting object will be approximately the sum of the two masses. And if this goes beyond the maximum mass, this is supposed to not be supported and collapse the black hole. But thanks to its rotation, because I mean, in this merger event, a lot of things happen, and this is even more cataclysmic than the collapse of the star. It can be supported for a few tens of milliseconds, where it will emit a lot of gravitational waves. Then viscous effect will take over, and maybe if we are lucky enough, in the end, it can go to a stable neutron star. But at every step, this might collapse to a black hole. Anyway, the point is, we try to detect, we want to detect the gravitational wave signal from this stage. And once again, the NBK does not do this, and this is the point of future detectors like Einstein telescope or Cosmologie, which is respectively European and American projects. Right, so we want to do hydrodynamics to be able to predict this. And actually, in the last 2 or 3 decades, people have been doing a lot of hydrodynamics for supernovae and neutron star oscillations. And these codes, they rely on what we call conserved variable. I'm going to show them just right after. You can also choose a bunch of different discretization. There are a lot of techniques. And the point is that these conserved variables, they allow the treatment of shocks. So if you do that, you can first do this narrow. This is easy compared to the merger, but you can go back to the merger, have the shocks, and predict what happens until this merger. This is very useful for NBK. But there is a but. This, let's say, the conserved variables are defined in terms of some physical variable that you need to know in the code. And this is really computationally expensive. So let's say we want to skip this. I'm going to just try it. Yes.
So I see that in the different discretizations, you list also smooth particle hydrodynamics. Are there smooth particle hydrodynamics code that work in general relativity?
Yes, there is one that is called Sphinx BSSN, which is developed in Hamburg. And I think it has been under development for like 10 or 15 years, but it was published only 3 years ago, 3-4 years ago.
I see. And if that's reference, that is there?
This reference, right?
No also the full value and then I was trying at some point.
Yes, but I'm not sure.
Now I don't know if that.
The difference is maybe that he's using CFC and the one of Rosberg is BSSN, so full general relativity.
I think you can see what it's restricted, but it's wide.
Yeah,
More than 45.
I know, and this is one of the points, but
Yes. So it's
you are really ahead of TikTok. Okay, so people have been doing that, and to illustrate that this is really computationally expensive, in 2 decades we have 500 merger simulations, which is quite all right, but in 2 decades it's not enough to do a parametric study. If you want to launch a lot of simulations with a lot of different matter equations of states, you have to build a code that is light, not too memory hungry, not too computationally heavy, and so that's what I'm going to show. But first, let me show you what are these conserved variables. So you see, these are some really nonlinear functions of some physical variables. So you have the mass of the variant, the variant density, internal energy, pressure, some velocity field. You have the different factor, which is really once again nonlinear function of the velocity field. But what's really neat is that these variables, they obey this simple function, which is partial derivative with respect to time plus the divergence of the flux, which is equal to some source. And with that, you have even more numerical representations that is communicating between hydrodynamics and the metric solvers. But you really need, at each step, to go from this vector of conserved variables to the set of physical variables, which we also call primitive. Conserved. And these variables are needed because they explicitly enter in Einstein equations. Also, if you use finite volumes discretization, which a lot of people do, you solve some Riemann problems in every grid cell at every time step to do some reconstruction. So this is again more computation. So let's say we don't want it. And what if we were able to actually evolve directly these primitive variables? So this is the goal of IKG. The point is, okay, we want to write, I say full GR, but it's not full GR yet. To evolve hypermassive or supermassive neutron stars, so they are not hypermassive yet, but they still rotate. And we want to extract these gravitational wave signals and try to do a parametric study, being able to vary these equations. So we want it to be really lightweight. So there are a lot of things we want to do. And one of the tools is that is written in C++ and based upon Lorraine, which is a library which is developed in Nano for the past 2 or 3 decades to represent neutron stars numerically. Yes. No, it's not CADAT. I think old is not the right word. I would say that CADAT, yeah, stems from Lorraine, but it has really taken different paths. And there is no hydrodynamics in CADAT. Well, there is none in Lorraine, but my hydrodynamics module was based upon Lorraine. Right, and so I have built step by step. I have the Newtonian simulations in spherical symmetry. I will not show them. Relativistic simulation in spherical symmetry. Actually, there is already a lot to say in spherical symmetry. I have developed some numerical tools to use this multi-domain approach, which I'm going to explain with different domains, which I'm going to explain why I need it. And finally, some axisymmetric and non-axisymmetric simulations to extract gravitational waves. As you may know, okay, so what's in the book? So we chose spectral methods for several reasons. First, the main reason is that, well, Lorraine is built on spectral methods, right? So that's the point, saying we want to build on what's existing and it's based on spectral methods. But why Lorraine is built on spectral methods is because you have an expansion of any say, scalar field on some basis of radial and angular variables. But what you could know here is that actually these numbers n, they are really small when you compare these two finite volumes. You can say there is easily a factor of 10 in every direction. So if you have 3 simulations, you're already getting 1,000. If you manage to have a factor of 100, you would win a factor of 1 million in all 3 districts. There is one caveat of spectrum methods, is that there is what we call this Gibbs phenomenon. If you have a discontinuity and you try to represent this with spectral representation, well, what you see is that this spectral representation will be oscillating. This is something you cannot overcome, which means we cannot treat shots. But it's all right. What we say is we don't want, well, oscillation modes of isolated neutron stars, so this should not produce shoots. And the way it's done is that you have several domains. So first you have a kernel or nucleus, which includes the origin. This is all spherical coordinates. Then you can add a bunch of shells, and then we can add an external compactified domain, which is really useful. So you make this kind of change of variable inside, and this brings spatial infinity to a finite point, which allows to, as we will see later, impose boundary conditions exactly at infinity, and not, you don't have to like cut your domain at some say arbitrary distance, which is high, but this is actual infinity. So yes.
So you may mention after, so there are kind of basic equations. So
I'm going to show that. I'm going to show the metric equations and the hydro equations. Because the hydro equations, they are new. And well, since they are primitive variables, I'm going to show them and show what's inside.
You mentioned about this assumption in background metric.
Well, the background metric is well, it's internal symmetry. Well, you are well.
Sorry, I'm not expert around this. So
Right, yeah. But
probably you saw the answer equation. So
yes.
It's not all kinds of matrix, so it should be certain.
I'm going to show that I'm using 3+1 formalism. Do you know? Because this is going to be the next slide. Yeah. So what we just okay. Right. This is for numerical representation. There is one thing that we must be really careful about, it's aliasing. So actually, you can represent your function by either its values on the grid points or with the coefficients. However, if you, well, the point of spectral method is to say, okay, we use the coefficient. But if you do that, performing a multiplication is actually a convolution in the coefficient space, which is much more expensive numerically. So we say, okay, we want to save this, and we do everything, every multiplication in the physical space. It's just point by point multiplication. But there, in this case, aliasing issue can appear, and so it's illustrated here. Basically, if you don't have enough points to represent, say, a sine wave, you can have another one of lower frequency to go through your points. And this is what happens if you don't have enough points there. But this is fixed at the beginning of the simulation. So you have to keep this in mind. You cannot always go as far as you want to solve. Okay, so we took this in mind. Now, to take general relativity into account, we use 3+1 formalism. There is a bunch of technical stuff in there, but what's really interesting is this picture. So what you do is you slice your space-time in, so you foliate it actually, and you have these surfaces which are constant level surface of time. Each surface corresponds to one time. And then there are some quantities, so like this n, which is the Laplace function, and beta, which is the shift vector, that tells you geometrically how to go from one slice to the next. And this is really useful because you separate time and space, and this allows you to naturally perform numerical simulations. So you do a bunch of geometrical operations, and the Einstein equations look like this. Okay, I forgot the important thing. The blue circles, they are second order terms, and the red squares or rectangles, they are products of order one terms. This means that all of this is very, very nonlinear and is once again a justification of why you need the computer to solve it. The rest of the terms are matter, and they come from the particular energy volume that you choose. I'm going to show this just right. You do some more stuff, and in the end, you have this set of equations, which are Poisson equations. So the point is you have elliptic Poisson equations. There is one approximation in there which actually kills the radiative degrees of freedom, but Lorentz comes with built-in solvers for this kind of equation. So at each time step, if you know, so on the right, you see that there is this E and S and a lot of other things, but if you know the matter content of your spacetime, you can deduce the metric. There is also this bit about the uniqueness issue that I don't have to go into, but this is what's implemented in the code. And this is where imposing boundary conditions on exactly infinity is important, is to solve these Poisson equations. Right, so this is for the part, the metric sector, the Einstein equation that tells you what the metric looks like. But then you want to also have the hydrodynamics equations. So let's assume that I'm going to show you the zero temperature equations. And we derive them for the perfect fluid, which is like this. So in reality, neutron stars, they are not perfect fluids, but it's already a mess. So we start slow. A lot of quantities, blah, blah, blah. This is not really important. You start from conservation principles, and you add an equation of states that closes the system. You do the calculation, boom, once again, big equations. And what's important is those terms. You have some, okay, this is the general relativistic primitive variable version of the Euler equation, which tells you how the velocity of fluid evolves. You have this advection term, which is what's another generalization. This gradient of the Laplace function acts as the gradient of a gravitational field. And you have here a gradient of big H is some enthalpy, and this acts as a gradient of pressure. So basically, you have the competition between gravitational field and gradient of pressure that tells you how the fluid evolves, and the rest is mainly geometry. Not only, but mainly. You have the same for enthalpy, which is kind of a generalization of continuity equation or conservation equation. And all of this is closed by the equation of state, which enters through the sound speed. And the sound speed is really, at least experimentally symmetric configurations in the room temperature, the main quantity that will govern the oscillation. And this is covariant, which means that, okay, I will apply it to self-radiating fluids, but actually you can apply to any configuration of the perfect fluid you have in mind. Right. So we have the set of equations. This is not yet, right? Perfect. So now I have shown you the model, and I want to show a bit of all the numerical tricks I have put in the code to make it work. But first, let's see the results in spherical symmetry. So spherical symmetry, everything is radial, depends only on one variable. And the first trick that we implement is that we introduce a mapping, so which tells you how the numerical variable in every domain is related to the radial variable, which is physical. And what we do is that we say that in this kernel, disk psi will be modulated by the radius of the star, which means that the differential operator has changed, which makes this derivative of the radius appear. And you have to add this equation. And then what's cool about this is that if you know the radius at some time, you will know it at the next time. So you know it throughout the whole simulation. Then another thing that we do, and that was already implemented in what I have shown, is that we use this enthalpy, because if you don't, you have vanishing ratio of vanishing quantities, which is not good directly. Some blah blah, and then we had trigger this oscillation with a perturbation, which is arbitrary and okay, so one test that has to be performed to see whether the code works or not is convergence test, which allows to highlight the orders of the numerical schemes. So on the left is the numerical the time scheme, which is explicit integration, which is order 3. So you fix the number of points, you vary the time step, blah blah blah. You get a slope, which is still 3, corresponding to the order of the integration scheme. No, it's imposed. It's imposed. Actually, so the next version, the next thing I show is the full 3D code, and the oscillation modes are recovered by the full 3D. But this is for the next step. And right, the other important thing is the order of the spectral methods. So on the left, it's log-log, but on the right, it's semi-log, and the y-axis is log. And you see that if you fix your time step, but vary the number of points inside the star, you have a slope, which is going down actually exponentially. And spectral methods do that. They have this exponential convergence, which is why you don't need so much breakpoints to represent the star. So this is one validation. The next validation is the migration test. So the principle of this is, okay, so this curve is the mass of a static configuration, strictly symmetric, non-rotating, with respect to the central density that you choose to compute your initial data. So you will have a curve like this, and on the dashed side, these configurations are unstable. But what happens if you still choose somewhere a configuration that is somewhere on the unstable branch? Well, there are two outcomes possible. It can collapse to a black hole. This is what happens in real life. Or if you do this numerically, it can migrate to the stable configuration with the same variant mass. So conservation of particles has the same variant.
I got confused. So you said in real life, it collapses into a black hole.
Yes.
But in the simulation,
it can
migrate.
It can migrate. Actually, you cannot predict what happens if you just choose a random configuration. You can put it in the code and see what happens. One way to ensure that it collapses to a black hole, and this is going to be the next test, you can add a perturbation that makes it above the maximum mass. In this case, it will always collapse to a black hole. But with one particular configuration that has been studied, well, the migration test was performed, and my code would also produce migration. However, it will crash around 1 millisecond. And okay, what I say is I still believe in the beginning of the simulation. I have to shift the curves to match them. The black curve has been produced with the coconut code, which passes brilliantly this migration test. But what happens actually is that when this crashes, there is a shock. And you remember primitive variables, spectral methods, no shock. So, okay, this crashes because of the shock. I still trust what happens. And another important point is that this is a really highly general relativity configuration. So supposedly solving for the metric takes a lot of time. And the spectral code will take 10 seconds to reach this point, while the coconut code will take minutes. So you see, lot of time gains. Right. Next. Yeah, right.
More about this, because I see this in other modes. So imagine that you just put the unstable configuration there on the stable branch, and you don't put anything but just a variable.
This is my
error. Right. So if you run the same simulation, well, the same configuration several times, several simulations, can you get the output?
I don't try to like
You can force like getting a black hole adding a little bit of mass, for instance.
Yeah.
But I was wondering if just kind of the uncontrollable numerical error could lead to different.
So what I can say is that every time I run this, it led to a migration. I have not tried to see if it could lead to a black hole, like not touching anything. So I don't know, maybe.
I think it depends on the numerical level.
Yeah, maybe to the
That will
PowerPoint.
depend on things like failure, resolution.
Yeah, this is not really predictable.
Like say changing the resolution, you could have in principle different outcomes, even for the same initial name.
So let's say in another way, you may add some different noise that can activate oscillations different. That I am not sure.
Right.
But for example, so let's say the amplitude can depend a lot on the noise you introduce. But then the frequency is more regulated on the intrinsic properties of the macroscopic. Then I would not expect difference in.
Yes, but I mean, you don't compute the frequencies of unstable configurations anyway. No.
Well, the reason I'm asking is that for some models, say of boson stars, you see something very similar, at least I'm more familiar with. And it's not something you control that well. So if you're on the unstable branch, I mean, there are uncontrollable issues that might dictate if the outcome is actually migration over the
Does it depend on the noise, or do you have some local minimization?
If you have something,
Let's say your questions are well posed from a mechanical point of view.
yes, because you're just using a system of equations which is all closed, but that's in the continuous. So there's a discretization issue.
Okay. Yes.
And this introduces errors, noise, and that we do not control that well. That depends on the infrastructure it's set.
Yeah, I am just saying this because the previous slide that I presented was original conformal calculation. Now we are using something called extended. This shares a lot with the conformal in some ways of analysis, for example. And that, in that case, for a very compact object, you have problems of local minimum. And what you have is you have transition to something that has same volume, total volume mass, but completely different configuration. So that's why I'm asking you that
I see.
you
We have a more fundamental problem there.
Yeah,
even
yes,
in the
okay.
continuum. Yes.
Yes, so there are two things. One is about the numerics
Yeah.
that you need to control, but there are also, and I have seen this several times.
I see. Well,
Like
I think
computing very, very compact configurations, you need to.
they need not be terribly compact. You know, I mean, I'm not sure what the compactest number would be, but yeah, I as far as I was aware, the issue was noise, which you don't control. If you go to the continuum, the system would be well posed in principle, at least in the Einstein boson. Yeah. But again, the question is, even if you don't change the resolution, if you put it there, are there uncontrollable sources of noise that would lead, even with apparently the same infrastructure, to different outcomes? So that would be my question initially.
Yeah.
Sorry, but
It's okay.
maybe it's just multi-dip.
Cool.
When I have another question. So here, you mentioned that the code crashes because of these shocks that form, because the code is not able by design to handle this continuity.
Yes.
But actually, even the usual state, it has a discontinuity that is at the surface of the neutron star. No?
Yes.
But how do you?
Where there is a domain boundary, which allows you to follow the exact directions. And so actually, this could be something to be implemented to perform this to the end, to say, okay, when the shock appears, we put a domain boundary at this point, but then you have to be able to follow because actually the shock is moving towards the area of the star, so you have to be able to follow it, and so since, well, okay, we trust this, to say, okay, let's do something more important. Because this is not very physical, it's a physical test. Well, the referee did not complain too much. Right. Okay, so the next test is testing the strong gravity regime. So now you do the same, but ensure, so I think it's the same configuration, but as a perturbation so that it collapses to black hole. And what happens is that you can measure the central lapse. It goes very low down to a few tens to 96. And what the lapse does actually is telling you how close one slice of space-time is to the next. Which means that when it's really low, you really have this strong dilation of time. And the second thing that is notable is that from there, we use an apparent horizon finder to say there is an apparent horizon, which means there is a black hole formed. So this indeed went to a black hole. And this means that the code is able to handle really strong gravity. Right. I think that is my subject to speed up a bit. And then, okay, so this is just a bunch of numbers, but what you have to look at is the percentage, some configuration you can make them oscillate, extract the frequency of the same radius, take for the transform, have different modes, extract the value of the modes, compare them with literature, and find that the code is really good at it. In circle symmetry, the CFC that I very quickly mentioned is not an approximation. So in this case, let's say we don't test this. Right. And also I have done the simulation in the Cowling approximation. This Cowling approximation says, okay, fix the space-time at the beginning of the simulation. You don't solve Einstein equations. This accelerates a bit. Sorry. Yes.
Standard in this type of test, in this literature,
Where
this test comparison.
So the digits of the references, I don't remember how long they run the simulation for. I took what's in the papers. But for my extraction, I would say that yes, the digits are really better because I run the simulation for long enough, so that the Fourier spaces.
In this literature here,
Yeah, they do.
Comparisons is enough. For example, to give 1.4, 1.4, 1, you will get higher precisions.
People show this numbers and sometimes they do. So I would say yes, this is usually. Okay, so this works well, and now we can turn to higher code. So I come all the way to Portugal to butcher one of your words, which is, I say Roxas, I'm sorry, which means relativistic oscillations of non-existential neutron stars. This is the least far-fetched thing that could find to get this acronym. Now what we do is that we have two different ways for the general code. One that is dedicated to solve for the metric, yes, with only spherical domains, and a compactified external domain, which is the one that goes to special infinity. And then there is going to be the hydrogrid, which is one nucleus that remains spherical, and then an arbitrary number of shells. And what happens is that I'm going to show a picture just right after. We adapt the hydrogrid to the surface of the star. Why? Because you want to solve, simulate rotating configurations, and when it rotates, you have centrifugal force that forms your sphere. There is some more things I'm going to show, and all these techniques have been first validated on the scalar wave equation. Not really interesting. It's just Gaussian packets moving back and forth in the finite domain. And I have done all the same but Newtonian equation. Okay, so it looks like this, and actually the hydro grid looks like this. You have a bunch of different radial directions, and you have this nucleus that is spherical, and then the external shell, there is one in this case, will fit exactly the surface of the star, which you know because you compute initial data, and that will tell you the surface of the star is at this particular spot. Right. Then you have to introduce, to do this mapping, more equations. What is important here is that this mapping, once again, makes this kind of terms appear in the differential operators, and this introduces aliasing. If you remember, I introduced this a long time ago. But we have to cure this with filters I'm going to show right after, and there is a co-moving grid. Once again, the grid will exactly follow the radius of the star, which introduces an additional partial differential equation. And this one is actually fine to do. Whatever. Right, so you have to use filters, too much text in here. Basically, you apply an exponential that will smooth your spectral representation because you want exponential convergence. So in log scale, you need to have something straight, and this is what the filter does. We do it. We have to introduce regularization scheme. So if you want to use spherical variables, you have seen on this before that all these angular directions they meet at the center. So we have a number of points which are numerically different but physically the same. So in principle, they should represent the same thing and not diverge. If you do it naively, it will diverge. And the same happens on the vertical axis. Right, so we have to introduce things to cure this. And the last really important ingredient is what's the so-called well-balanced formulation. So what you say is that your quantities have some perturbation that is not necessarily small, but you can plug this in the equations, and you have a bunch of conditions that allow you to remove the equilibrium terms. If we only use UI and H directly numerically without this extension, this would be, of course, fulfilled, but up to some numerical precision. This can introduce noise, which you don't want. So if you don't have that, you can have longer simulations and more precision on extraction of frequency oscillations. Right, so I also mentioned this very quickly, but CFC kills all radiative degrees of freedom. So if you want gravitational waves, you have to resort to, say, other tools. So we use the stress formula, which was popularized by Einstein. This is a second time derivative. We don't really like that numerically. So what we do is we use this stress formula, which allows to replace the first time derivative with some special derivative, which are really easy and precise with spectral methods. And I have to compute the second derivative by hand. Then there is plus cross decomposition, and in the end, you can extract from this the gravitational waves. So it looks like this. This is for one particular equation of state, which is a polytrope analytical equation of states, rotating quite fast, as more than almost 700 Hertz. So you see that you have this signal, which has some spectrum. You can identify some of the modes. Once again, so, okay, on the one side, there is a mode, which I'm going to compare to literature and see that it's fine and we're happy. But on the other hand, we have this gravitational wave signal that can be useful for both detection and parameter estimation of astrophysical source in the data analysis for Einstein telescope, say. At this point, it's not really realistic because it's not a realistic equation of states. It's only rigidly rotating. It's not hypermassive. But when the code is realistic enough, the point will be to have these gravitational waves signals as templates that data analysis could use to infer all the information they need about the equation state of the neutral star, like the post-normal neutral star. Right, so once again, a bunch of tables which tells you that this works fine. There are a bunch of models that are really highly rotating and you don't really extract the frequency, but this is because they are really low frequency. I could only go to, as you see on this, 25 milliseconds, which is not enough to extract some of the lowest frequency. But the point is that we are able to extract the quadrupolar modes, which are the dominant one frequency, gravitational wave oscillations. Which, by the way, might not look like it on this, but this is an arbitrary perturbation and not a realistic one. Right. Okay, so let's try to conclude. So the code is spectral and it's dedicated to evolve isolated neutron stars and rigidly rotating at this point. It's based on a set of equations that relies only on primitive variables, which is new. A number of numerical techniques have been implemented. This is all the struggle of the PhD is inside there. I was able to extract some non-axis symmetric mode frequencies for a bunch of equation of states and extract some gravitational wave signal. I did not have time to go into this, but I also studied out of beta equilibrium. So you activate again electron captures and neutrino emission. The outcome is that at 0 temperature, it does not change anything. And the code so is very light. I have not said this, but the 3D simulations, you can run them on your own computer, laptop or office computer. It is sequential and it still has reasonable simulation time. So what I have shown takes, I say, less than a week. There is no recovery procedure, which enables the reasonable simulation time. Well, one of the reasons, say. The radius of the star is followed by a grid, really important again. And well, this allows to have a really precise frequency extraction, for example. And although we have used this conformal approximation, the table of numbers that I have flashed actually show that the extraction of frequency is really good, despite the fact that we use this approximation. What we are comparing, the numbers with were extracted in full general relativity, which means that this CFC is okay, seems to be nice, and we don't want to get rid of it too early. The code is public, you can find it right there. This is the paper, this is the code. Of course, it has drawbacks, no shock treatments, as I have shown. I would say that spectral methods are unforgiving because you do the slightest mistake, everything will crash. And it's only oscillations of post-merger phase, so you can't do much with it, but it has a very specific goal in mind, and it's supposed to be very good at this. And what we are going to do next is, okay, getting rid of CFC will have to be done at some time, but okay, no priority. We need to be able to perform longer simulations, so long-term stability of this, well, supposedly good configuration. And this is a postdoc is working on this right now to implement differentially rotating profiles. So what they do is they perform merger simulations. Then you stop it at the moment of the merger. You extract the rotation profile, and being able to put this in on SAS will be like a step to go further in the realistic simulations. And I leave you with the code name.
So we still have time for more questions. Yes, well,
So you were extracting gravitational waves with a particular approximation here. The first piece is just the leading term that was in my approximation. So you have an argument that this is good, that the following of terms are expressed.
Well, I would say the frequencies of the signal are matching the ones that are extracted over
Yeah, so
which is
that's our
the first argument. Then I would argue that yes, we should go beyond that. maybe if we do, we will see that it was sufficient. And
Oh, there are some simulations going beyond.
Yes,
that
but-
shows you that the most extreme cases, you are losing the 4 significantly.
so I would say right for the frequencies, but what about the waveforms? This I don't know.
Well, but you said at some point you'd like to start with initial data coming from a simulation of two merging neutral stars. So depending on how deformed this is, then I would say the dynamics could be quite strong and perhaps,
So we have put on Valencia, let's say the extension, the natural extension, and the difference is very, very, very small.
but wouldn't that depend, that's my
Maybe that's
question,
like an
on how close you are to an equilibrium solution, how big sort of perturbation is, because certainly in the merger, if you analyze the merger itself, and if you analyze gravitational waves just by polar approximation, that wouldn't be
So
good.
listen, for the merger itself,
Yeah,
I expect more difference.
Yeah.
Then I expect a lot of shocks, and then time for those space. But once, let's say you have more or less one object,
but that's exactly my point. It's
Even
how
if
much
it's
more or
very
less is
small.
more or less, yes, exactly.
then what
Yeah,
once the shocks and all the stuff more in the merger phase have passed, and you don't really use this kind of technique, because in the case of shocks, basically you cannot use it. So you are, and it's not only the difference in the CFC formulation, it's also about the shocks and all the dynamics in the market. Once you have this hypermassive object, even if it is extremely rotating, and in this case, we compute it, so-called something like, okay, compute this remaining part, and it's really very small. You need, maybe in your configurations, I don't know, because you use this compactness, but you really, for example, in the colors of this neutral code, you really need to be very close to the conventional black hole to see significant differences.
right, so exactly, so my point was that if you have, say, a supermassive star, in some scenarios, it could actually collapse to a black hole.
Yeah, but
And then you wouldn't expect that just a protocol approximation would be a good approximation even. So,
Also, some ultra simulations, they go beyond that and run the first one, right? Not a lot of them, but there are some. So it could be
yeah, and also CFC is exact in spherical symmetry. So you need to deviate from spherical symmetry and very compact.
Right.
If it is very compact, but close to spherical symmetry, it's also okay.
Yeah, but hypermassive will be so.
Yeah. And the difference, we are working on that, but it takes time.
of course.
But it's a very honest and fair question. But I can tell you, you really need to go to extreme cases to see a difference that is not comparable to numerical language.
Yeah, Hector?
Okay, good. I have two questions, actually. So the first one is that you have already shown that the code performs very well in the test. So I am not doubting about the usefulness and the accuracy of the code. But I was thinking, compared to finite volume methods, finite volume methods have two nice features. One is the treatment of discontinuities, and the other one is the conservation of quantities that are supposed to be conserved. So I wanted to ask how well the code performs in regard of this second feature.
I don't remember. But basically, it does perform well. You can check for observation of, say, median mass, and well, it depends on how good the perturbation you put, but it will be conserved to less than performance.
I see now. Right. So
And even in spherical symmetry, it's really, really good. Like, it tends to extend, like, of course, if you put a big perturbation, but yeah, all the conserved parameters are really good.
see that's very nice.
Yeah.
And the second question is that if you start having differential rotation in the star, it is possible that you will trigger the Kelvin-Helmholtz turbulence. And so my question is how do you expect to see an advantage to typical 5-volt codes for which it is already challenging in
Yeah,
this kind of control?
I don't know, maybe it's why it's
Yeah, no, you're completely right. Once you have this development of jobs, you need to really focus on STEM's able to catch that. But also in that regime, people think that I would ask if they are improving viscosity in a proper way. And then we can also cover that.
Yeah.
For example, if you have shocks or these interactions, you need to go to something that captures these shocks. But then mechanical viscosity, I think, will also play a role, and it is not physically properly included in most books because of the complexity.
Spectral methods are not in their case.
But there are, well, I am also working on that, and there are new ideas from our mental control. But this is as always, as far as you can reach, and then check the differences are strong or not to be significant for your purpose. Because the limitation, computational limitations will create a reduction.
Well, so when Cosmologie is working on this launch simulation, so I guess that we will start. But I don't know.
Thank you. Yes, Eugene, please.
The question toward the end, was another slide, for comparison, relative differences.
Yes,
So you can see, I think if some of them are very, very well.
some of them are high, yeah,
What was the, you are comparing your results?
with some tabulated papers. Well, that would give tables with their own extraction. And yeah, I could go into what they do and yeah, is a lot of
And what is
numbers.
the reference? The table that you use as reference for the paper from
No, it's Kruger and Kokodas.
about
Any question online? Doesn't look like it. Are there more questions here?
I have a curiosity. So when you were mentioning supernova 97, well, I kind of gathered that you were debating the outcome was a black hole
yeah.
or a neutron star. Could you expand a little bit on that because I was curious?
Well, we know that approximately one solar mass was neutralized, but approximately is really approximately, like I think around 180. And so we don't actually know the mass of the object. And I think we didn't have any observational evidence until recently of what was the outcome. And you can safely say it's either a stable neutron star or a black hole. But I think there was a paper some months ago that showed that might be one of the two when we found it.
So there is no consensus according to what you know in what is
Not a clear consensus, but it's starting to be less shady.
in which direction?
I don't remember. I'm sorry.
Okay, let us know when you.
Maybe I have just a quick point that the frequencies that you're extracting are in the detectable band for like machine telescopes, say, or
Yes.
but not
Like-
LPK, I guess.
Not LPK, like
remnants
LPK
are not visible.
would go to a few hundred hertz,
Mhm.
but then if you go to 1 hertz.
But so the things that you see already, they are in this
Yeah. Yeah,
frequency band.
actually, you're right. I could have said that this is supposed to be detectable by actually that much with the current sensitivity skills. Okay.
Well, then we can thank Gaël again.